think that's a great habit to have, trying to upskill on the weekends. I'm sure it will do great benefits to you. Today, we will be talking about machine learning and petroleum data analytics, but it will be unlike other webinars that I've done till date, because we will talk about more of the practical aspects and directly jump into the projects. I'm sure I'll try to explain things from scratch, because that's what I try to do. Please feel free to, hit me up with your doubts or any questions, be it any level that you think it is. Don't be shy of asking me anything, because we are great petroleum engineers, but yes, some of us are trying to learn analytics, and it can be no doubt is really very, very dumbed out. You can ask me anything. If you want to ask, just type in the chat, or maybe wait till the end, or have a quick discussion with me. Or maybe if you feel like I could not clear your questions, you can write to me on LinkedIn and we can have a discussion about your doubts. So we will try to do a few projects, and during those projects, the way I've structured or planned today's session is we will talk about basically every tool that we use in data analytics. We will talk about it in project terms, so that you know where these tools are used. If I'm talking about NumPy, giving you an introduction about NumPy and then using it, you don't really get a feel of where it is actually used in practicality. No point spending too much time on theory when you can directly jump into practicals. And that's what I feel. I want you guys to, if any one of you is starting their journeys in analytics, I want you to have a bold approach to it. Just hit it bang on. Just try to fight the analytics domain with projects, and you will definitely get stuck at a lot of places. You'll be like, hey, how do I do this using NumPy? Hey, how do I plot this plot? But there is always Google at your disposal. You can always search things, and that is what someone nicely said. The best skill to have as a data scientist is to know how to Google your problems, right? And that's why I don't think the modern generation has to spend too much time, unless and until you are mathematically sound. You give the algorithms a nice understanding based on the mathematics, then you are good to go. You are good to apply your skills. These days, you don't even need anything. By the way, I have not shared my screen yet, so don't worry. These days, you don't need any hardcore softwares to download to run Python on. If you don't have a fancy computer, which was the case with me 2 years back, I used to practice it on a simple laptop that I had on Google Colab. Everyone has a Gmail account. You can use Google Colab with it, and you can write whatever code I'll be talking about today. You will always have the liberty to practice on your own. Also, the good thing about the sessions that I do is everything that I talk about is always there on my GitHub repository. So even if you are skipping on something, you can always go back and try to refer to these topics and maybe have a better understanding. Or if you have doubts, the better thing is I'm always there on LinkedIn. So you can always, try to talk to me about it. So let's get started. This was a quick, heads up and a quick, motivation behind how this session can upskill you a great deal. And I hope it does. And let's get started. We will be looking at simple analytics projects, talk about a bit of math, talk about algorithms. I'll do a bit of whiteboarding in front of you, try to draw a few diagrams, try to explain you things in my own handwriting. And then we will also come back and do the coding again, right? So I'll share my screen now. Let me know once you can see it. Okay, let me share. Can you see my screen?
Yes, we can see it. Thank you.
Perfect, brilliant. So like it says, welcome to the project-based introduction to petroleum data analytics and machine learning. Okay, you want to get a feel of where things are used? Here it is, right? The agenda is we will look at the following projects. I've lined up decline curve analysis on wall field data. I will not directly jump into the wall field data set. I will first explain you how this optimization, the brilliant scientific package in Python, which is called Scipy, is used. If you are not familiar with anything that I'm talking about, I will explain you as I go on with it. We will talk about how mathematical optimization is carried out which is nothing but a fancy word for curve fitting. Everyone has read about curve fitting in their schools, but I will give you a simple example first on how to fit a equation that you know on the data that you have, right? And then we will get on to the actual data set on wall field from the field data set. Or maybe if I don't think it's wall field, I think it's Norwegian field, I guess, a non-field. So I'll check on that. But anyway, we have field data on which we will practice decline curve analysis. Why I'm putting this as the first topic is because before even you get into machine learning, you need to have a perspective about what machine learning is and how machine learning is different from something like a curve fitting, right? And this project will exactly tell you how about the case where we did not know the equation. How would we have done the things? What if I just had the data set and not the equation, the ARPS models? What would I have done then? That's when machine learning comes in. So that's my motivation behind starting with decline curve analysis, right? And the brilliant thing, one of my favorite topics, which is also useful for, if you understand Scipy optimization, you read the documentation of how mathematical optimization is done using Scipy. You can build your own algorithms, machine learning algorithms from scratch without using fancy packages, right? So that's the great advantage of looking at decline curve analysis. Then we will talk about exploratory data analysis on the wall field data. My aim behind this is to tell you what kind of things that a data analyst or the data scientist goes through. Now that I've spent enough time in the field, I know that majority of the project timeline, it goes into spending time cleaning, making the data happy, making the data look well, making the data good enough to suit your machine learning algorithms. If you are in a good company working with a good project, and on the second day of your project, you are like, sir, can I fit a random forest on this data? Your manager will laugh at you. He'll be like, that's not what we want to do right away. That's not even the important part. Machine learning comes at the end, at the very end. If you want to be a data scientist, you need to understand the end-to-end workflow of preparing and making the data good enough. Even if your data is good enough according to you and you fit machine learning algorithm in it and you have 99% accuracy, I'm 100% sure that there will be flaws if you haven't spent much time on the data. Why? Because you need to think about a lot of conditions. You need to think about what will be the impact of failures from this model. You need to think about what kind of values this model can expect in the real world scenario. You always have to think about the consequences. You have to run a lot of permutations and combinations inside your brain to decide what kind of data you need to have, what kind of algorithms you need to have. Sometimes you'll be like, oh God, this is not enough data. I need to have more features. I need to have more information. So you need to go back and collect more data, or maybe ask your manager to conduct some experiments to get more data or something like that. So unless and until you are confident that you have covered all the aspects of the project, you cannot just directly jump into machine learning. And that's why the second project is very important. I know it's a machine learning training, but machine learning comes at the very end. And that's why my machine learning parts are there at the end. Of course, based on the interest of time, I might be skipping a few if I run out of time, but you will have this notebook by the end and you can always have the reference. And I'll just clarify all the concepts that you need to know before you run these projects, right? So you'll have a regression problem in front of you. You will have a classification problem. And this thing, the forecasting problem, is one of the first times I'm conducting. I've never taught forecasting in any of my projects, in any of my webinars, but forecasting is one of the most important concepts. You can use it right away on, let's say, production forecasting or something like that. All right, so all in goodness, let's get on with it. Okay, so the first step before you even talk about anything, before you do anything, is to import all the necessary packages. If anyone here listens to rap music, hip hop music, they know who Marshall Mathers is. But most people call Marshall Mathers using his pet name, which is Eminem, or the way it is popularly called. This is exactly how we import packages in in Python using during machine learning or before machine learning. There are packages or tools, people call them tools also. There is NumPy, which is like the Marshall methods, but popularly it is called NP. So you always import these packages with their reference names or their pseudo names or their alias, right? You don't use NumPy as, I mean, you can use it, but you don't have to. People call Eminem as Slim Shady as well. So you can import NumPy as simple N as well. That is also going to work, but make sure whatever you specify in this particular section, use the exact name throughout the code. Okay. So I've run this before to prevent any wastage of time. So the tools that we need in any data analytics project is NumPy, which is basically, it's like a calculator tool in Python. The calculations that you do in your calculator, the logarithms, the trigonometric functions, the exponentials, anything. I mean, you know, the Laplace transforms and stuff like that, linear algebra, anything can be done in NumPy. So it has a lot of mathematical capabilities, okay? Maths and stuff. I'll write that down. Pandas. What's Pandas, guys? Pandas is the Microsoft Excel of Python. Okay. It is built on top of NumPy. Remember, guys, just to give you a heads up, NumPy is built using C++ as the coding library. Of course, it is a Python package, but behind in the background, it is built on C++. You don't need to code in C++. But why I'm telling you this is because NumPy, because it is on C++, C++ is one of the fastest programming languages in the world. And that's why NumPy is one of the fastest tools in Python, right? So if you have two options, whether to do a calculation using normal Python code or to do it using NumPy, always make sure you do a calculation using NumPy. Even if the code becomes a bit longer, the runtime will be thousands and 10,000 times faster. Okay. So always remember, Pandas is the tabular, you know, it allows you to play with data like tables, etc. So whenever you will be importing any data set, your aim will be to convert that data set into a Pandas data frame, which is nothing but a Pythonic way of calling a table, right? Then there are two visualization packages that we need. One is Matplotlib, which is anyone who has worked with MATLAB, they will find Matplotlib plots very similar to the way they look in MATLAB. So MATLAB plotting library of Python is called matplotlib.pyplot. Okay. So Matplotlib is a MATLAB plotting library common to both MATLAB and Python, but there is a Python plotting package in it that is called .pyplot, and that you import it using the simple name PLT. Now, this also clarifies why we need these, reference names, because imagine if you had to import matplotlib.pyplot as matplotlib.pyplot, you will have to write the huge word every now and then whenever you use it. But now, because you've imported it using the reference name, it becomes simple. Seaborn is a statistical plotting library in Python. You can do histograms, beautiful looking distribution plots, etc. in Seaborn, statistics plotting. Okay. And I will give you a use case for every of these packages. Anyone, any doubts? I see someone talking.
Could you please explain again what the matplotlib is? Just for fresh, I didn't really get it.
I'm sorry, are you asking, you need an explanation on what matplotlib is?
Yeah, just a refreshing.
Yeah, I mean, it's coming right ahead. I mean, we are starting. So I'm just giving you an introduction, and we will look at various usages of these plotting libraries. So just be with me for the next few minutes and you will see. All right. Okay. So there are a few more packages like Scipy, which is scientific Pythonic library, which helps you do advanced mathematical calculations that you need, like Fourier transforms, a lot of things, Gaussian normal distributions, writing. You don't need to write these advanced formulas by your own. Scipy has them inside it, right? So that's why Scipy is very popular. Scipy is basically used in a lot of machine learning libraries in the backend So Scipy is one of the most popular languages as well. Math is also one more, but most of the things that you will see in math, they will be in NumPy as well. So you don't need to use math because, like I said, if you have two options, always go with NumPy. All right. Okay, let's start with decline curve analysis. I will give you for someone who asked about matplotlib, you will see right here how it is used, and let's talk about it using projects. Okay. So what decline curve analysis is? The aim here is to understand how we can use Python to fit a model or an equation into a data set that we think must follow a physical model. That we think, it's not think, but think. Okay. Okay, let me draw a few diagrams and come right back to this model. And for anyone who does not know about decline curve analysis, let me clear how this project will be going about in the backend. Okay, so can you see my whiteboard? Or do you still see the Jupyter notebook?
We still see the Jupyter notebook.
Okay, I'll share right back. Just give me a second. Here it is. Here it is. Screen. Okay. Yep. Now I hope you see it now.
Yes, we can see it now.
Okay. So the project one here is decline curve analysis. Okay. I'll quickly give you an introduction what's going to happen here. Okay. So we have a data set. Okay. Q versus T. Okay. We have flow rate versus time data set, and this will be very noisy. You know, this data set will look like this. Okay. Very noisy data. It will, on the high level, you can see that it is showing some sort of decline trend. On the high level, you can see it is showing some sort of decline trend, but the original data is very noisy, right? And this is the data. Okay. This is the data. And you already know the equations like Q equals to Q naught e to the power minus BT, which kind of fit into data like this. But what is fitting? What is fitting? What does it mean? What is fitting? Fitting means to be able to find out these parameters, which are called coefficients or parameters or constants, whatever. These parameters will keep on changing from data to data. Okay. For one data set, it will be this. For another data set, it will be different. So we need to find out Q naught and B for this particular data set. And that's what we will be doing using Scipy. Okay. So that's what DCA is about in Python. And it is very easy. You don't need to do hand calculations by your own. You need to just create a function of this model. Then you need to import this data set. And then you need to pass both of these things inside an optimization problem. And that optimization problem will return the correct values of Q naught and B based on this data. The next day, if someone gives you another data set, you run the same code through that data set, you get different values of Q naught and B, and then you can fit Q naught and B to that data set. The third day, someone gives you another data set, your Q naught and B changes, the entire algorithm remains the same, and your model fits to that data set. But remember, guys, the good thing is, you know, this model here. You know, there are a few models like exponential decline, you know, hyperbolic decline, you know, harmonic decline, if you are looking at conventional reservoirs. Okay. So you know these models, and that's why this is not machine learning. This is not machine learning. Why? Because you know all this. In machine learning, you try to find all this. You have this in machine learning, but you don't have these models. You try to find these models. You try to fit, you try to ask the machine to figure out what kind of pattern this data is following. And that's why in machine learning, you always need a huge data set. But in problems like DCA, even a small data set will work because you know what kind of equation you are trying to fit into, right? So let's get back to our, I hope this algorithm is pretty clear. And now we will look at how to do it in Python. Okay. Any doubts, anyone, any clarification needed on DCA as a problem statement before we head into Python? I think it's pretty straightforward. So I'll directly jump into Python and then we will look at any doubts if anyone has. All right. So let me share my screen. Okay. Not sure where this went. Yep. Can you see my notebook again?
Yes, we can.
Okay. Yeah. So the first package that you need to import is called scipy.optimize. You need to import a package called import a utility called curve fitting, which is located inside scipy dot optimize. People will ask me why this dot is coming. So basically, imagine it's something like this. You have a huge folder, which is called Scipy. Inside Scipy, you have a folder called optimize. There will be other folders called linear algebra, etc., etc. So you need to open the folder called Scipy first. And inside Scipy, you need to open the optimize folder first. And inside optimize, you need to open a script, which is called curve fitting, which will have a lot of functions for curve fitting, right? That's why this syntax is from scipy.optimize import curve fitting. Okay. Now let's look at a simple example first, and then we will jump right into our DCA example. Okay. So this is the first introduction to how NumPy is used. So we are creating X and Y data, linear data, noisy linear data to match the real world example by ourselves, but we know the equation that we will be trying to fit. Okay. So what I'm trying to do is I'm trying to fetch random integers between 0 to 100. I'm trying to fetch 100 random integers between 0 to 100. And the way to do it is you from NumPy open the random folders packages, random numbers folder. And from that random numbers folder, try to use the randint function using which we are trying to tell it that, hey, can you give me 100 random integers between 0 to 100? And then we run this and we store it inside X. Okay. And then we calculate Y using this equation. Y equals to mx plus c, everyone knows, but I'm adding random noise to it. Okay. This is nothing but noise. Okay. This is nothing but noise. So you just import, you just create an X data, which is the X axis. And then you create Y data, which is the Y axis using mx plus c equation. Y is a function of X, and you plot the X comma Y. For someone who was asking how to use matplotlib, let me give you 5 minutes now. So plt.scatter does a X comma Y scatter plot. The syntax is very simple. You just use plt.plot X axis comma Y axis. Okay. So you can see PLT, because we are trying to plot a scatter plot, we are using plt.scatter. How about I wanted to not do a scatter plot? I just wanted to do a line plot. So plt.plot X comma Y. You can see a very noisy line plot is shown here, which is not a good way to show. That's why we go back to the scatter plot. So that's as simple it is, right? It's no rocket science, very simple packages, nothing else needed right now. Okay. So we have the data. We know the X and Y data. It looks something like this. All we need to do now is figure out the slope and the intercept. We already know the correct values of slope and intercept. We know that slope is 2 and the intercept is 3. Now let's find that out using curve fitting. Okay. Okay. So we first create a function. Like I told you that we will have to create this function, right? Something in the decline curve, we will do a hyperbolic function or something like that. So here, because it's a linear model, we create a function called linear model. Okay. The inputs are X. Now, this is another introduction how to create functions in Python. Okay. You need to specify a def keyword, and then you specify the function name, and then you specify what kind of inputs you will need inside the function, and then you calculate the output, and then you return the output. A quick introduction about function, that is. Let me give you, for someone who does not know how to use functions, let me create another function for you. Def. How about I wanted to create a function that would square a number? Okay. So I will name that function as squarer. Def will always be there. Def squarer. I'll pass in a number and I will return what? Return the square of this number. Now, I told you that whenever you have an option of using NumPy or any other thing, if you need to use Python, you can use NumPy, number to the power 2. Power is given by 2 star symbols. But because I have an option in NumPy as well, NumPy.square num. Okay. Now, the way to use this is I'll just use the squarer function and I'll pass, let's say someone wants to do a square of 4. You can see 16. Okay. Similarly, you can create a cuber function and stuff like that. Just an introduction on how functions are used. So suppose I had to square 2 numbers, number 1 comma number 2. So I'll return the square of number 1 and I will also return the square of number 2. Okay. So square, now I'll have to provide two numbers, 4 and 10. And you can see, yeah, because I have not, yeah, you see the square of 4 and 10 is returned. Okay, quick introduction about functions. Let's move on then. So I have created the model that I want to fit. This is the way to tell Python what kind of equation you want to fit in this data. Okay, and then you pass the equation that you want to fit inside this curve fit function. There are three inputs you need to pass. The linear model, which is the equation you want to fit. If you are running DCA, you will have to pass the hyperbolic model or the exponential model. You need to pass the X dataset and the Y dataset. So the Python knows that what is the data I'm fitting this linear model into. Okay, and then you run it and it returns parameters. And the first element of these parameters will be the two important things that you need. The two important things that you need is the slope and the intercept. Okay, and then you know the curve fitted value of slope and intercept. And you just let me just see what kind of MNC the function has returned. You can see M according to Python based on the understanding from data. M is 2.017 and intercept is 2.0908. So let me see. You can see the slope is pretty good, but the intercept is not that accurate. Intercept is 2.0908. And why the inaccuracy is there? It is because of this huge random noise that we are added, or maybe because of the lesser amount of data. Only 100 data points we have provided. Python was not able to conclude enough evidence. So I'm hoping that if I provide 1,000 samples, the accuracy of the performance will be pretty much good. Okay, let me do a bit of that in just a while. Okay, so that's a very important concept to understand, guys. This is your clear understanding. This is in front of you that machine learning or any analytical projects, they will fail when the data is not good enough. It is still fine. If I show you a plot, you can see the plot is looking pretty good. The red line is the predictions and the blue dots are the actual data. It is still able to understand pretty good. Yes, we can see that the intercept is quite falling apart, but the original overall fitting is pretty good. You can see the red line was just found out using curve fitting. Okay, you are passing the calculated values of M and C, not the actual values inside this linear model. And then the red line is the model predictions and the blue line is the actual data. And there is not so much difference. It is able to understand a high level trend and the intercept that the data is following. Now let's run that experiment again on more number of data points. Let's do 10,000 data points. Okay, 10,000. And because there are 10,000 data points, I need to add noise for those 10,000 data points. We run this again. You can see now it is so crowded. We run, this was just an example. We run all of these things. And there you go. You can see now my slope is also very much close to 1.99. My intercept is also very close to the actual intercept. The actual intercept was 3. The actual slope was 2. The calculated slope is 1.998, which is almost 2. The actual slope intercept is 3.06, which is almost exactly 3, approximately 3. So I hope this clears a very important part. As soon as I increase the data, the calculations became very good. Now let me decrease the data. Okay, let me reduce the data and you will finally have a proof why data quantity is also very much important. So less. Okay, you'll see my model performance will fall down drastically now. I'll run this again. I'll run this again. I'll run this again. There you go. Look at the intercept, guys. Look at the intercept. Terrible. You came down from 100 to 10 data points and you could see the model performance has now fallen drastically. Okay, so that's the problem with machine learning. We are not yet at machine learning, but we can directly see that if you don't have enough data, any algorithm will fail because machine needs to have data, good amount of data to be able to tell the story. There you go. Why we are able to see that something is matching is because it is trying to match the noise as well. And noise is not the actual data. Okay. So in 10 data points, you cannot differentiate between whether it's a noise or anything else. So let me go back to 100 now, and we will move on to the DCA project. Okay. If it is too simple for you, great. You are already doing good in data analytics, but I'm trying to go for everyone in the audience. Everyone must learn something from this session. And that's my hope. Okay, brilliant. I hope everyone understood the basic workflow of curve fitting and optimization. Anyone wants to ask anything? If not, we will move and do the same thing for actual data set, oil production data set or gas production data set, and do the hyperbolic curve fitting on that. Anyone wants to ask anything? I see something in the chat. Okay, thank you. Someone said it's perfect. Anyone, any doubt? Feel free to either unmute or type in the chat. Anyone, let's take 2 minutes and then we will move forward.
Can you please show the code again? Just the coding part again. Okay.
Sure.
So a quick question. What does line 71 speak about?
What can you repeat? What are you talking about?
Line 71.
Line 71. This
Yes.
one, right? Yeah. So what happens is curve fit. When you run this curve fit, right? This is a function like you saw here. I gave you an example here, right? So if you run squarer function, it returns two things. Okay. Number one, the square of number one and the square of number two. Now, what if I just wanted the square of number one as the output? I need to find. So it is located at the 0th position, right? You can see 16 is located at the 0th index and 100 is located at the first index. It's like a roll number. In Python, indexing starts from 0. So the first element is located at index 0. So what if I just wanted 16? I would do something like this. And that's exactly what I'm trying to do here. So suppose I imported and I stored these values in a variable called squares. Okay. And using this, I just wanted the square of the first element because my aim was to print something like this. Okay. My aim was to print something like this. The square of the first element is, then I need the first element square only. I know both of them are stored inside the squares, but I need just the first element. So squares 0. And then something is wrong here. What is wrong? Squares. Oh,
You typed wrong.
Spelling is wrong. Yeah. So that's why, and the parameters is having the same issue. If I run the params again, PARAMS, you can see there are a bunch of things that it returns, but we only need this one. The other thing is not important. Okay. I'm not even sure what this was. I forgot. I don't have it on the top of my mind, but we only need these things. Okay. And that's why we just index the first element, which is the first array. And it is having two elements inside this array, which is the first one is the intercept, the slope. And the second one is the intercept. And someone will ask me, what is the ordering? The ordering is exactly the way you provide it inside this function. So suppose I had C comma M, then I would do a C comma M here as well. This would be C, this would be M. But because it is M comma C, Python follows the same ordering. And that's why we have M comma C. Okay. It is very straightforward. I understand it will be a bit of confusion in the webinar, in the live session, but if you have this notebook, you go back and look at it, you'll be like, yeah, it is relaxed, chill. So I hope I gave you a bit of context, right?
Yes, thank you.
Okay. Anyone else? Okay. Looks like we are all good. Let's move ahead. Next up, we are going to apply this understanding to an actual oil data set. Actual production data set, let's not call it oil data set because the rates here are in standard cubic feet per day. And that's why we are not calling it oil, because it's a gas production rates. Now here we will get a good chance to look at how to import data set using Pandas library, okay, and how to do a lot of indexing, etc. Pay attention on this. So PD is the alias for Python Pandas. Whenever you see PD, we are calling all the superpowers of Pandas. .read CSV. So again, like I told you, go inside Pandas, give me the read CSV function script or the function, and pass on these parameters. Okay. Now this is a code which is located at this website. The good thing in Python is you can directly fetch the codes from websites. So this is a code that one of my friends, Johannes Novara, I hope everyone knows him, great guy, brilliant tutorials he shares as well in Petroleum data analytics and geoscience. So great one to follow. So I borrowed this code from one of his tutorials that he had shared. Of course, we can also do this on wall field data set, but I thought, why not use a simpler data set first, right? And so that data set has two columns. One is date column and the other is rate column. But whenever these kind of data sets which have one column called date and time, these data sets are called time series data sets. And always remember, if you are trying to import a time series data set, always make sure that your date column is always the index column. You don't need the date column as a separate column. Okay. So what I'm saying here is, if you didn't do this index column equals to 0 and parse dates equals to true, the date column would be showing like a separate column here, and the index would be 0, 1, 2, 3, 4, 5, the default indexing that happens in Python. But that's not the right way to import a time series data set, because you only store those columns in the column format which you want to do calculations on. Date is an index, date is a reference. Why date is there is because you need to reference when is this flow rate happening, when is this event happening, is my flow rate 19207. That's why date is always in the index. So these two parameters, what they are saying is, the 0th column that you find in the data frame, call it the index, and make sure you convert that date, everything becomes a date time object. Okay, because by default these 2004-04-01, because of these dashes, it becomes a string. It is interpreted as a string, a collection of characters, which is not the right way. It is a different data type called datetime object. So nothing else, no rocket science, just these two columns are a necessary way when you are trying to import a time series object, time series data frame. Then we are just printing the top 5 rows of the data set, and this is how it looks like. So this is the step 1 is how to import data. That's the first step you will do in any data science project. You will try to import a data set from a source, and the source is provided here. It can be a location in your computer as well. It can be location in your websites as well. Why I'm using a website source here is because the location will not be the same in my computer as it will be in your computer, but the website will always be the same. So if I share this notebook with you and you run this code again, it will run. Okay, brilliant. So next step is we need to visualize whether it is the correct data we need. We are trying to model a decline curve data, right? So if there is no decline, then we can expect that this is not the right data set. This is called a mini level exploration, data exploration, right? So the way we do it is first-hand visualization. Nothing, you just pass the data set name, which is DCA-DF, which is DCA data frame, dot plot, okay? Dot plot, and you just pass the figure size, which is 12,4, which means the width of my figure will be 12 and the height of the figure will be 4, because I want to show a flat kind of figure, right? And then I also want to see grid blocks, okay? And then when I plot it, you can see this looks pretty good, okay? Everyone would agree that this looks pretty nice to be modeled into a DCA model, okay? I can see a nice hyperbolic fit. If anyone has worked with DCA models, they know that the data sets with a huge tail like this one, they are good candidates in hyperbolic models. And this is where people cannot just go ahead blindly by data science. They need to know petroleum engineering as well. Because if you are not understanding the DCA models correctly, you can try to fit exponential model in this, which is fine, but not the best option. So there is a bit of homework that you need to do about various decline models also. If your model is, if your data set is conventional reservoir, you need to have models like logistic growth or power law model or something like that, which are pretty complex, but they are for unconventional reservoirs. Okay, but this, I think this is a good candidate for hyperbolic decline. Now let's follow the workflow. But there is a problem here. The problem here is we don't have the time variable. We know the Q variable. Remember, guys, I showed that we need the time variable. Currently, what we have here is we don't have this. What we have is date 1, dates, date 1, date 2, date 3. We need to convert all of these to time 1, time 1, time 2, time 3. Okay. The origin right now, the origin is the starting date, which is, let's say, January 2015. But can you feed the date time objects into a DCA model? No. We have to convert the first date into, let me change the color. We need to convert the first date into 0 and the second date into delta t, third into delta t plus delta t, and so on. And that's how this axis will become a continuous time axis. And then we can feed and follow the same algorithm again. Okay, let me go back. All right. So again, if someone wants to see a scatter plot and do some beautification, which is not important, but I like playing around with plots, so have it, don't worry. Okay, so like I said, we need to convert. I see people are waiting. Admit all. Okay, yeah. So the first step is to convert the time axis or the daytime axis into continuous time array. Okay, so this is the function that does this. This is again a nice advanced practice on how to use functions in Python. Like I said, that's how we are going to do today. We are going to look at all the concepts by projects. Okay, so day maker is the function name. Always make sure you give the names correctly, which you are able to understand later on as well. So we are passing a data frame inside this day maker function. Okay, and like I said, it is going to run over every time index one by one, and it will be calculating a delta t from the first time. Okay, so suppose January 2015 is my first date, then February 2015 is my second date. So my delta t now becomes 30 days. March 2015 is my third date. So my delta t will be March minus January. So there will be 60 days and so on. That's what this function is doing. So I'll have to iterate over every one by one date. I'll have to iterate, and I'll have to calculate the difference between that date and the first date and store it into this delta. And then I'm returning, and I'm storing all these deltas inside a list, which is this one. And then I'm returning this entire list. Okay. And then I'm storing this list as a separate column. You can see my date now is converted to a days column. You can see, like I promised you guys, the first date is now the 0th day. The second day, you can calculate. Let's give it a try. What is the difference between first April 2004 and 1st May 2004? What is the difference, guys? It is, of course, 30 days, right? So you can see the days are 30. And again, one by one, you are calculating the difference. Now we have a continuous days column as well. And now we can use these two columns to do a DCA modeling. Okay, I'm plotting the same thing again. You can see plt.scatter. Y-axis is this one. X-axis is this one. Marker is nothing but the shape of these dots. And my color is nothing but green. Again, a nice practice of matplotlib, plt.scatter. I'm specifying the figure size as well, plt.grid as well. You can see, I can see my decline now pretty good. Okay. And the good thing here is we have now converted the x-axis to days. You can see my initially x-axis was date time, but now my x-axis is just a continuous format of days. All right, fair enough. Let's move ahead. Now, you will find this very familiar to the one we discussed just 5 minutes back. Okay. The first step is we create a function. Everyone knows a hyperbolic function. Hyperbolic function is nothing but q equals to qi upon 1 plus b dit whole to the power 1 by b. That's not important. We are not talking equations right now, but every petroleum engineer knows what a hyperbolic model is. Okay. And the constants in a hyperbolic model are qi, bd. I understand some people call b as d and d as b, and yeah, I don't want to get into all that. But my aim is to give you an algorithm that is robust enough to be run on multiple data sets. So right after you get done with this webinar, go back home and try to practice this on a Wolfield data set released by Equinor. Okay. And I'm sure this will work on that as well. Right. And that will be a great win for you. I mean, if you are in your undergrads, you can call it a mini project and, market it around and people will be happy with you. How about making an app of it? On my LinkedIn, you will see that I've created a DC app and people have accepted it very well. So it's mini projects make a lot of sense, right? Now, what I've done is all the different steps that I was talking about, I have put all of them inside a single function so that I don't need to run all those steps again and again. I can just call this hyperbolic fitter function and it will do all of these things. And now everyone, please pay attention. We are going to look at a very important aspect of models. Okay. Remember that here the modeling magnitudes are so huge. We can see my x-axis magnitude is very small. It is in 0 to 1000, but with every gas wells, the flow rates are pretty huge, right? It is in SCF per day, which is very, very huge. I mean, 2.5 multiplied by 10 to the power 6 compared to 100. So the model will be bamboozled. It will not be happy because it won't be able to, optimize really well because the magnitudes of one axis is so huge. The magnitude of the other axis is so small. There is no homogeneity. So it is always advised in machine learning or any modeling problem. It is always advised that you focus on normalizing. Okay. Your focus must always be normalizing the data set because otherwise the optimization will either be too slow or it will not be able to converge really well. Okay. In order to reduce the error magnitude, you need to make sure your magnitudes of the data are pretty small. And I'm using very simple way to normalize it. My aim is to bring everything to a common range. So I'm normalizing flow rate by dividing it by maximum. I'm normalizing time by dividing it by maximum. So both of these flow rates and times now are in 0 to 1 range, which is very good because if your data, like Scipy algorithm has to deal with smaller magnitudes, it does really well. The performance is really good. And later on, you can just multiply it back again with maximum and maximum, and you are back to the original magnitudes. That's no worry. Okay. So you have the original data, which is Qn and Tn, normalized versions. And then you pass it inside curve fitting. Like I told you, there are 3 things you need to pass inside the curve fit function. The first thing is the function that you had created, like the linear model thing that you had created. Right now it is Q hyperbolic. So you pass that Q hyperbolic, you pass the x-axis, you pass the y-axis, and then it returns parameters. The first 3 elements of the parameters in the same order as this one, they are important. You fetch those in, and then you again calculate the same thing again, and you pass these optimized parameters inside the hyperbolic function, and then you run it and you return the Q hyperbolic fit, which is the model predictions. And you also, just for safety's sake, you also return the parameters, right? And after all this is done, which is pretty straightforward, I have explained you all, there must be a few manipulations you might need to do, go back home and do it. But let's summarize it by plotting it. Okay. You can see the brown line is the model performance and the green line you already saw was the actual data. So you can see how brilliantly we have fit. And like I told you, the tail is fitting really well because that's the major identification of a hyperbolic model. If you had an exponential model, you will see that the initial stages were fine, but the later stages would be maybe overestimated or something. So a good selection of correct decline model is very important. So a quick caution at the end is, notice that in this DCA technique, which is physics-based based on ARPS models, We must know the equation prior to the project. Suppose I told you we don't have this. Would you be able to run the curve fit? Because the first parameter you need in a curve fit, apart from the data, is the model. If you didn't have this data, this entire thing was nothing but a garbage, right? So that's what I'm trying to tell you. We need to know the physics. Otherwise, we cannot do anything. Whereas in data-driven approaches and machine learning problems, we normally start with only data, just this green part of the data. We don't know any assumptions about the physics, nothing about it. And we fit the model that suits the best. And this is the use case for production forecasting. Okay. One problem with this DCA modeling is, suppose you had a stimulation happening at, let's say, t equals to 800 days. And my dots, the green dots, they spiked up. But the original decline trend was established and my model would predict lower rates, but my original rates would be high because of stimulation. The DCA models cannot identify sudden changes in production rates. Okay. If you have run a production enhancement property or something like that, your DCA models cannot perform really well in that case. So I wrote a LinkedIn post back in days about the problems about DCA in noisy data sets or in stimulation or shut-in projects. In that case, DCA was failing really well. So I think it's from the wall field only, well number 12. If you run this model on that data set, you will see that when there is a shut-in, the DCA model performs bad. So that's about the first project. Congratulations. You have done your first data analytics project in Python. Anyone who does not have Python in their notebook, I'm running it on Jupyter Notebook, which is a product of Anaconda. You can either download it or you can use the same code on Google Colab. Okay. Moving on to the next project. Let's take a 2-3 minute pause for doubts. Anyone, any doubts, any points, any worries? Feel free to ask.
Could you please hold the screen on the code again?
Sure. This one? Yeah, this is important. Yeah, let's focus on this.
One question. In this code, can we call it machine learning because we're finding the parameters and not using the?
No. We cannot. This is nothing but an optimization problem. We are just trying to minimize the error because we know the correct model we are trying to fit. All we need to do is take this model and fit into the actual data. So I'll give you what's happening here. Okay. And what happens in machine learning. Okay. So what's happening here is, let me draw ugly diagrams in front of you. So you have this data here. Okay. I'll draw the noisy data. This is my original data. Okay. The decline data. And I'll use a different color for, so, and this is my initial version of the DCA model. Okay. The data is here. The model is here. There is a huge error. Okay. So what optimization Scipy does is it runs multiple iterations. So in the next iteration, this model comes here. In the next iteration, it comes here. In the next iteration, it comes here. And in the next iteration, it goes here. So it knows the error is increasing again. So it again comes back here. And in the final iteration, it's something like this. And by the time it reaches the final and it realizes this is the minimum error case, it tries to figure out what was the initial QI, what was the B and DI, etc. with respect to this fit. And then it returns these things as parameter 0. But remember, we already knew, right? We already knew this was the model. We didn't just directly feed this data inside the machine and ask the machine, bro, tell me what's up. We are providing the thing that we already know. We are fixing what we already know. There is no new thing we are doing. But in machine learning, the way machine learning deals with things is it will take, let's say, 100,000 examples of this blue line, and we'll try to, understand the pattern. Now, why this is important is because what if I told you that, let's say, in Antarctica, ARPS decline models don't matter at all. They are terribly fitting. They are terrible. But we still need to do production forecasting. Would you be able to use DCA there? No, right? So what can you use there? There you will use what is known as machine learning, because trying to understand something from data with no assumptions at all, no assumptions. No assumption. It is a technology that will work throughout the globe, throughout the universe. Suppose tomorrow you had to run DCA on moon. You can do that as well, because you have the data on moon. All you need to have data, you can do DCA on moon as well. But will ARPS decline models fit on moon? I'm not sure. So that's the basic funny philosophy behind why machine learning is so popular, because assumptions keep on failing every now and then. There can be no scientist in the world who can have one model that fits the entire universe. But this technology, because it has no assumptions, it just looks at the data, tries to understand the data. It can do pretty okay. It can be terrible. In cases, it won't be as good as DCA is. But the good thing is, it is able to perform at least fine decency in everywhere. DCA will fail terribly. Like I told you, if there is a well with a field having 10 shut-ins every 2 months, the DCA model will not be able to forecast well at all. But if you provide the shut-in history to a machine learning model, machine learning will understand how a field production behaves when the well is shut in. It will understand the patterns after shut-in, before shut-in, and something like that. And anytime in the future, if you are trying to ask, what is my performance? If I expect some shut-in happening, tell me what will be my forecast. It will show a spike in the forecast as well. Where DCA would keep on declining. DCA would be like, oh, hey, that is too late in the life of the field. I think the flow rates will be around 0.5 barrels per day. But originally, because your shut-in was happening, machine learning, because it has looked at 100 shut-ins in the history, it will be like, hey, I think it's okay. I mean, the decline says it is 0.5. That's all right. But you are saying that you are going to shut in. So I think I'll give you 100 barrels per day at least. So does that clear the story, how it is different from machine learning?
Yes. Thank you.
Okay, brilliant. Can anyone please add people waiting in the room? Some people are, because while I'm talking, I just miss them. I don't want anyone to miss the session. So yeah, let's move ahead. Anyone, any doubts? If not, let me go back to the notebook. All right, now we are going to talk about the second project for today. Again, no machine learning involved, but this is like 90% of what a data scientist does. He keeps on looking at the data, visualizing, doing plots, reporting analysis, something like that. So I'll tell you one of the recent projects that I did. I had to look at these visualizations like I'm looking at, thin sections under a microscope. I had to zoom into the visualizations. I had to analyze the signatures, the trends of the sensors, etc. I had to make sure whatever I'm looking at is trying to tell something or not. I had to be a literal scientist in that case. And then I felt like a literal data scientist. Machine learning is not the fun part. Data science is the fun part. Playing around, understanding, making sense of the data, trying to convey a story from the data. That's where the heart lies. And that's what this second project is all about. I see something in the chat. Okay, you're welcome. Okay, so, right. So again, like I told you that whenever you are trying to import a time series data set, you will always have to pass these two things, which is again what I'm doing. This is a data set located in my GitHub repository. Originally, it is a data set released by Equinor. It is nothing but the wall field data but people find it difficult to download the Waldfield data set and stuff. So I have stored it in my GitHub repository. You can just run this code and you will have the data set in your notebook. All right. So you have this notebook by the end of the day, you run it. All right. So the first step is again to look at, this data set, the plot all the columns of this data set and try to do some data science. Try to look at the data like a detective will look at it, right? You try to look at some kind of stories that this data will try to tell you, right? We are trying to tell the plotting package that, hey, can you plot this using subplots? Let me remove this and you will understand why this is important, okay? If I remove this and if I run this again, you can see everything is now stacked. That's why I passed that concept. All you see is this huge magnitude production rates, right? Which is not everything that you want. You want these features as well, right? So I just pass this again and I run this again. And there you go. You can see all the columns are now in their own separate subplot. Okay. Figure size is 12,12, which is horizontally 12, vertically 12. Now let's look at all the features that are there, which is the first step of your data science project. You look at all the features that you have in the data set. Again, the first step is different actually. You do a df.head, which is printing the first, let's say 5 or 10 rows of the data. And you can see this is the first 10 rows of the data. You can see my index column is again this one. And I have all of these columns with me. Okay. Now let's say I just wanted to print all the column names. So I just run .columns and I have all the columns. So what kind of columns I have? The first column I have is, by the way, in machine learning terms, columns are called features. Okay. I have all these features. On-stream injection hours. So I think there is an injection well in this field corresponding to this particular production well. And this feature is trying to tell you what is my on-stream injection hours. So what if I just wanted to plot this particular feature? So I'll just pass on-stream injection hours, Control C, Control V. This is the way to access a column. Okay. This is a way to access a column. So you can see now I have a single column printed and then I will do just dot plot. And you can see this is my plot and I'll change my figure size because I want a flat looking plot. Fig size equals to 12, let's keep it 3. And you can see this is so basically my injection rates are pretty consistent around this 20-25, right? I'm injecting at a pretty, it's not a rate, but the hours. You can see there are 24 hours in the day. So the maximum capping is around 24. And you will see that a lot of days your injection was not that great, but a lot of days your injection was carried out for whole 24 hours. Okay, so you can see here. So this is the way to plot a single. So there are other columns, bore WI volume, which is nothing but the injected volume of water. On-stream hours, which is a production on-stream. How much in the day, how many hours in the day were you producing? There is an average downhole pressure. So you can expect a proportionality between on-stream hours and oil production, which is bore oil volume. So if you plot these two things together, you will kind of see a proportionality between them. So let's do it. How about we do it? That would be a good practice for matplotlib as well. plt.scatter df. On the x-axis, I will keep on-stream hours. And on the y-axis, I will keep df, bore oil volume. Let's see what it looks like. You can see it is kind of an increasing proportion as the, the oil production, the production hours increase, the oil production also increase. Let me, whenever you see some kind of messy plot, try to normalize the data. Max divided by max of this and divided by max of this. That's called pre-processing of the data. You can see you can keep on playing the way you like. Nothing is incorrect. You can have your own techniques. I did not plan to show you this, but now I'm doing it because I started thinking like a data scientist. So as you keep on doing, you start thinking like a data scientist, right? So in this one, I'll have to provide the bore oil volume, and I run it. Does not make any difference. So I think we should skip this part. But the good thing is we expected a proportionality. We see a proportionality. Okay. Let's see the relationship. And if you want to see what is the magnitude of this correlation? There is a way to do that as well in Python. So you just run df.core, which does nothing but it prints the inter-feature correlations. Okay. So you can see on-stream injection hours is 100% correlated because every feature is with itself, it has 100% correlation. But let's look at just what bore oil volume, how all the features are related with bore oil volume, because that's our output feature. Oil volume is what we want to predict, right? So you can see we were looking at on-stream hours, right? You can see 0.36 positive correlation, which is trying to tell you that for every increase in on-stream hours, there'll be kind of 36% increase in the production rate. It will be an increment. But there is this feature which is saying that there is a negative correlation. Bore water volume has a negative correlation with bore oil volume, which is again by petroleum engineering knowledge. You can confirm this by knowing exactly what it means. If your water production increases, your oil production decreases. Simple material balance, right? So that's how all of these things get connected. And I'm spending time on these things because I want you to know your petroleum engineering knowledge will play a key role in petroleum analytics, jobs in the future. Let's look at a few things now. Let's look at this bore water volume. It's increasing steadily over the course of time, and then it drops. Okay. Oil volume, it's showing a nice decline. So if you had to do a decline project, you would have pretty good results in this domain actually. But where DCA would fail, like my dear friend asked right now, why machine learning is important and DCA can fail, is around 2014 and 15, when there was this huge spike in this production rate. DCA would not be able to predict the spike because machine has only understood ARPS model, and ARPS model says that because it has started declining, it will keep on declining. Now, someone will ask me why this spike was happening. Maybe just look at exactly in the parallel, look at the choke size. It has increased so much. And that's why I think the choke size increment caused a spike in production. I think so. But what if there was a shut-in also? Because I see that my production rate kind of dropped before the choke size increased. So maybe the well was shut in for a long time, because I see my gas rates also dropping. I see my water volume also dropping. So every flow has decreased. So that means maybe my well was shut in, because I see the choke size very close to zero. So how beautiful is that? You can tell a nice story behind why this spike happened. In one of the courses that I conducted, I always ask these questions. I don't care about what machine learning model you're using. I want you to tell me why these kind of stories are happening. Even if it is incorrect, I don't care. There are a lot of incorrect posts on my LinkedIn, but I try to do a lot of insights from the data. I don't care if they are correct or not, but by data science points, you can be correct because you're just analyzing, right? You can see your wellhead pressure is also increasing. So something is definitely happening around that time. By looking at the data, you can clarify. Other things that you need to note from that data is something like anomalies. So you can see if you look at bore water volume, it has almost a consistent value, but around this time, something was happening. Maybe this was an anomaly. So in machine learning, before you feed this data into a machine learning model, you always need to handle this errors in magnitudes or the outliers or anomalies. Okay. So try to analyze this first and tell stories. That's exactly what we were doing. Okay. Now, next up, we need to look at nulls also, because your aim is to prepare this data to be ready for machine learning. Machine learning cannot work with nulls in your data set. It cannot work with empty values in the data set. So there are ways you can calculate how many nulls are there in your data. So you can run df.isNull.sum, which does nothing but it calculates the sum of nulls in every column. And then you sort these values, and then you plot a bar plot. You can see it is showing an empty because everything is there. None of these fields is null. You can look at it again. SNS.heatmap. This brings in Seaborn now. Seaborn SNS.heatmap df.isNull. It will show you the entire data set. This is a top view of the data set. It's like your Excel sheet is printed and you're looking at it from the top, and it shows a color coding. Okay. So if it is a null value, it will show a different color, something like a white color, but now it is not showing because we just saw There are no nulls in this. So your data set is good enough to go in terms of nans. You don't need to fill your data set. If there were some null values, let's say, let me figure out, let's say my bore water volume had null in 2008 or 9, something like that. What should I do there? I should do some interpolation, because I already know the 2000, I know 1 year of trend. I can see from my eyes that this trend is continuously consistent from last 1 year. If there is a few rows which are empty, I can just use this trend and fill for those values. This is called data processing, the pre-processing. You are trying to fill for null values. Never drop, always try to, prevent dropping the null rows as much as you can. Always try to fill them by using various mathematical techniques. You can do hit and trial. You can run one technique, see if it betters your performance, run another technique, and keep going on, right? All right, that was nulls. Then we do some descriptive statistics to analyze if and when outliers are present. Okay. Now people will ask me, how can you look at descriptive stats and tell whether outliers are there or not? I'll tell you how. So I'll need to go back to my whiteboard. I'll try to draw a distribution plot here. Okay. So suppose I have this data. Okay. I have this data set. I have this Y column and I have this X column. Let's say X1 is my one feature. Okay. This one feature I pick up and I plot the distribution of this plot of this feature. Okay. And I'll use a thicker pen. Do I have a thicker pen? Okay. Oops. Never mind. So I draw a distribution plot. Okay. This is how my distribution looks like. And you can always use Seaborn to do this. Okay. This is how my data distribution looks like. And what my descriptive statistics will tell you will be, what is my 25th percentile of this data set? What is my 50th percentile, which is nothing but the median of this? What is my 75th percentile? Okay. Now this is a symmetric data set, so I don't have many outliers. But what if my right tail was, let me use a different color. What if my right tail was very long? Okay. My right tail was something like this, and there were values here. So my max will be, this is my max, and this is my min. So you can see my min is pretty close to my 25th percentile, but my 75th percentile and my max have a huge difference. And because this is a huge difference, these values can be called what? These values can be called outliers. And that's what I want to tell you. By looking at descriptive statistics, what you can do is you can analyze whether your data has outliers or not. Any doubts, anyone? Because this is an important part. We need to understand outliers and handling outliers. And this is a nice way to analyze outliers while dealing with your machine learning problem. So let me give you an example by looking at the notebook now. So on-stream injection hours, your 75th percentile is 24, maximum is 25. By domain, you can know that you can never produce 25 hours in a day because you only have 24 hours. So you need to check for these errors. Then you look at bore water injection volume. 75th percentile is 6,000, almost 7,000, and max is 9,000, which is fine. 0 is my minimum, and 25th percentile is 4,000. So you need to handle these zeros now because the huge difference is there in the left-hand side of the plot. So keep on analyzing these outliers in all of these features and handle them one by one. Okay. Or maybe create a function that handles all of them together. Right. So that's how df.describe gives you the descriptive statistics. But most of the people know how to run df.describe, but most of them don't know how to use it. So that's how you use it, df.describe. Okay. And there are ways you can use scaling also, because machine learning needs to treat every feature as equally important. But you can see my on-stream injection hours are around 24, 25, 0 to 25 in magnitude. But my oil production and injection rates are in thousands. So my machine learning model will be like, hey, I think water injection is a huge important value, but on-stream injection hours, because it is so small, should I ignore it? Should you ignore it? No, of course not. Choke size is very small, but 10 choke size is like almost open choke, which is very important for predicting oil rates. So you cannot ignore it. Just on magnitude, you cannot decide if you should ignore or not. That's why there are techniques that you can use to scale the data set, like you did in DCA. You scale the data set in 0 to 1 range, and you can create a function of your own. But that's your homework. You need to go back, and I'll also give you an example in the project. But there are ways you can scale the data set into a common range. You can use standard scaler. You can use min-max scaler. Min-max brings it to 0 to 1. Standard scaler brings it to a standard normal distribution. Okay. Brilliant. So this is about exploratory data analysis. A few things and few aspects we looked at: how to make use of your exploratory, how to be a detective in terms of data, how to make conclusions, how to handle outliers, how to fill for null values, how to scale data sets, and so on. So by this understanding, you are ready with the data science aspect of it. Now we can successfully use all of these knowledges and convey it to a machine learning project, and then finalize this training. So anyone, any doubt by now? Anyone about exploration?
Yes, Divyanshu, thank you for your explanation so far. It's been very clear. I have a question regarding the outliers. When you know that you are dealing with outliers, you mentioned that it's always recommended not to delete data. So how would you go about these outliers? Should you delete them, or should you try to fix them in order to have a better value of them? What's your recommendation to
Brilliant question.
Handling?
Brilliant question. Thanks for bringing that up. So I'll give you, again, by a picture, I'll give you an example. So let me draw a distribution. I always try to look at the bigger picture. And by bigger picture, I mean, I look at the visualization first. Okay. So suppose I draw the visualization, the distribution of my data, and look something like this. Okay. This is my 75th percentile. And this is my remainder of the data set. Okay. And now I know that my data has outliers. Basically, the ideal technique is you calculate the IQR, which is this one, IQR. Okay. Suppose this was 5,000, this was 1,000, my IQR now becomes 4,000. And if your data is lying, let's say 1.5 times of IQR will be 1.5 times of 4,000. Okay. 1.5 times of IQR, if my data is lying beyond 1.5 IQR, anything which lies here is my outlier. So my step one was figure out which of the data points to handle. So these black ones are the data points I need to handle, because otherwise they are pretty close to the, to the actual distribution. They are not, you cannot be so strict. How about they were representing some actual phenomena? Okay. So that is also you need to conclude, but experimentally statisticians have confirmed that something which lies either to the left or to the right, 1.5 times IQR, it is definitely an outlier. Okay. So these are the data points now you need to handle. Now I go back to my data set. I have this X1 feature, right? This is my X1 feature. So I have this, let's say my X1 feature was pressure. Okay. Pressure. And then I go back to my data set and I see, point out where these data points are located. And here are these data points are located. All of the others were fine. All of these others, the ticks are falling in the distribution, and these crosses are falling in the black domain. Now I need to handle them. Now there are ways to handle these. People, one way is you check your proportion. How many of these values are outliers? Suppose you have 10 million data points and only 17 or 18 outliers are there. Definitely go on and remove them, because that's like 0.0000001. So based on your use case, if you can afford to drop them, fine, that's okay. But what I generally try to do is I try to analyze pressure along with other features. Okay. Now this is, let's say PWF, flowing bottom hole pressure. Now everyone knows PWH as well, right? Wellhead pressure. Now PWH plus some delta P would be PWF, right? I will do some sort of math to calculate whether PWH is fine and PWF is abnormally showing some high behavior. which according to my physics knowledge or my reservoir production engineering knowledge would be. So suppose it was predicting 17,000 PSI, where it should be, according to this formula, it should be around 11,000 PSI. So what I can do is I can replace the 17,000 with this 11,000 by creating a simple function, and then I replace it, and this comes back to this distribution, the new values. So what I'm trying to do here is I'm trying to point out all these wrong values, trying to correct it using nodal analysis, and trying to replace them in the actual data set. That's using your domain knowledge. If you don't have any domain expertise, you are working on, let's say, some other field, then you can do some interpolation, right? So I'll give you an example of interpolation. Let me draw another diagram. Suppose my pressure is looking something like this, okay? My pressure is looking something like this. And okay, and this is my outlier. This is my pressure with respect to time, because it's a time series. So every time the x-axis will always be time series. Now you can clearly define what would be the correct way to solve this problem, because you know this is abnormality, this is an outlier. You can do some interpolation. And now again, if you plot the same thing again, initially the distribution was looking something like this. Now if you plot it, the distribution looks very symmetric. And that means you have successfully handled outliers. And you can see that in your model performance, the accuracy, the errors, the mean square, and they all drop down. So I hope I gave you a few examples on how to deal with outliers. Thank you for this brilliant question. Did I make sense?
Yes, thank you.
Brilliant. Anyone, any doubts? If not, let's move ahead. I think we only have half an hour more to go. So congratulations on completing the second project now. We have talked about how data sciencing is done with the data, and we have dealt with very nice questions as well. Now we are ready to apply all of these things inside an actual project. So next up, based on how much time we have, we will have 2 to 3 projects in front of us, and you will always be able to understand this, but I want you to be prepared to know what will be the problems you will be facing. Okay, I'm definitely confident that once you click on this link, you will be able to understand the entire workflow of a machine learning project, of a regression project, of a classification project, and of a forecasting project. But I want you to understand the important things. All right, so let's talk about regression first. So whenever you are trying to do some regression, let me teach you this in using diagrams. So let's say I have a data set x comma y. Okay, this is my x and this is my y. Now machine learning has two kinds of problems. One is supervised problems, one is unsupervised problems. Okay, so supervised problems means you know the correct answer in your data set. You know the y, and you also have the x, and you are trying to find this mapping between x and y. In unsupervised, this is not there. Y is not there. And you try to figure out on your own, you try to figure out what is the prediction or the classes that they belong. Today's session is not going to deal with unsupervised problems because in my experience, that's one of the rarest. I have not seen much of the use cases, but definitely down the lane, we can connect on unsupervised problems. Let's look at supervised problem. Regression is a supervised problem, okay? Linear regression. What is linear regression? So we have this kind of data structure, okay? We have 3 columns, x1, x2, x3, x4, okay? 4 columns, and I have y, okay? And for every value of x1, x2, x3, x4, I have a corresponding y, and so on. Okay? Now, how regression works is I will have x1, x2, x3, x4, x2, x3, x4. All of them combined together. X1 is multiplied by W1, X2 is multiplied by W2, X3 is multiplied by W3, X4 is multiplied by W4. And then some intercept is added, and they all give you what? They all give you Y predicted. Y predicted is what? Y predicted is W1, X1 plus W2 X2 plus W3 X3 plus W4 X4 plus B. People who know a bit of linear algebra can treat it like W transpose dot product of X plus B. So YP is nothing but W transpose of X plus B. And you also know, I'll use a different color, I'll use green for the correct answer. You also know the actual Y. Okay. And what machine learning does is, for every row, it will do this computation. It will calculate the delta between these two. J is basically the delta squared. What is delta? Delta is the difference between the actual and the predicted. Okay. So step one is to randomly give values to weights and biases, which is a fancy term for coefficients and intercepts. And you compute the Y predicted for that. You already know the Y actual for that. You calculate the J for that. You see how huge that J is. If the J is very huge, which means your loss is pretty huge, your error is pretty huge, you go back and you improve the weights and biases. You improve the weights and biases, and you calculate the Y predicted again. The Y actually you already know. You calculate the delta again. You calculate delta, you see whether delta is huge again. If it is again huge, you go back, improve weights and biases, again do the loss calculation, go back, improve weights and biases, again do the loss calculations. You keep on repeating these things till you have reached to the optimum value in a method called gradient descent, which is a nice terminology to know if you in the future look at neural networks as well. So I'll just give you a high level overview. So this, you can imagine the graph of J versus, let's say, J is a function of what? J is a function of W and B. Let's call both as theta. Theta is nothing but the variable components of the model, which is a combination of weights and biases. So on x-axis, if I give you theta, on the y-axis, I'll give you J. The optimum point where the model learning stops is at this point where the loss is minimum. Okay. And the training procedure, it follows a lot of steps. Okay. It starts here where your first random initialization of weights and biases will give you a huge loss beyond the universe. It will be terrible. If you go ahead with this, your model will be breaking a lot. So your model assesses how far it is from reality. If it is too far, which is at this point, it takes a step. It improves the theta. Your theta initially is this, theta I. It improves the theta, it goes here, your loss decreases. So it's like, okay, I'm going in the right direction. It improves it again, the loss decreases again. It improves it again, the loss decreases again. You are trying to climb down this mountain. Sometimes you'll climb to the other side, then you will climb back to the other side, and then you'll reach. And because the slope of the minima is almost zero, you'll realize that even after 100 repetitions, your model performance is not increasing. So you conclude that this is where I need to stop my training, and this is my theta optimum. And this is what a linear regression model will returns. And this is your completion of machine learning training. And you take the new data, you use these parameters which the model has returned, you evaluate Y for those unseen data sets. So that's about linear regression, the algorithm as a whole. There are a few assumptions where linear regression will not perform really well. Let's look at those assumptions. The first assumption is features must not be intercorrelated. Okay, features must not be intercorrelated because you can see for anyone who has worked with matrix algebra, you have seen that AX equals to B is the kind of thing that you are trying to solve. And if X is equals to A inverse of B, right? Or here we are trying to find A, right? So A will be equals to X inverse of B, something like that. This is a raw assumption I'm trying to tell you. What if my X determinant was 0? Then this problem becomes unsolvable. And you might have read in linear algebra classes that whenever two rows or two columns are highly interrelated, it's like almost identical to each other. The determinant of this entire X matrix, it tends to 0, which makes this equation, which is pretty much similar to this equation, it becomes kind of unsolvable. So that's your first assumption, that your features are not intercorrelated. Okay. There must be a linear relationship, of course. If you are using a linear regression problem, your model should be linearly related. Homoscedasticity is nothing but your errors must not be sensitive to any specific ranges of X. Okay. If your X has to follow a particular range, it should not be that your model understands the lower X fine, but your model cannot understand the higher magnitudes of X. It's like your model is, it's doing partiality. Your model loves your brother, but your model does not love you. How would you feel in that case? Your model loves your elder brother, but the model does not love you. So you will feel left out. So homoscedasticity is nothing but trying to find out whether model is doing some sort of partiality. Your error, if it is a bad error, it should be bad throughout. If it is low error, it should be low throughout. There should not be any magnitude bias. Normally distributed features, I hope you understand what a normal distribution is. Your assumption normal distribution is because if you tell the model that, hey, look, I'm trying to tell you something, that every data set that you will find out, one good thing would be every column will follow a normal distribution. If you have any background, you will see that if X1 and X2 follow normal distribution, a linear sum of X1 and X2 will also follow normal distribution, which is the final linear regression problem. So basically you are trying to, in short, you are trying to tell the machine that, hey, everything that you should expect from now on is a normal distribution. The good thing about normal distribution is you can summarize the entire population by just 3 numbers, which is mean, median, standard deviation or variance. Once you know these 3 numbers, you can make any predictions. You can summarize a whole population. You can summarize 10 million data points in just 3 numbers if you know they are in the normal distribution. Okay, you can summarize like 96% data points in that distribution with huge confidence. So that's a lot of statistics, but I'm just trying to tell you that it's like telling the model that if you just can understand the distribution that the model is following, I'm telling you it's a normal distribution. Just try to figure out that what's the mean, standard deviation, and variance, so that in the future, whenever some new data will come, it will also follow the same distribution. So you don't feel like something is terribly new to you. Okay, that's my attempt to clarify the assumption of linear regression in the simplest terms. Okay, and let me go to the project now. I think I have it open somewhere here. Here it is. So in this problem, we are trying to do some linear regression problem. Okay, it can be failing also because I just mentioned the assumptions that a linear regression problem needs. And let's look at whether we can make oil production forecast using the same data. Just we did these exploratory data analysis on. We'll do some machine learning on it and try to see how we do machine learning in Python. Okay. Again, you can see the familiar culprits are imported. Again, the data set is also imported in the similar manner. You're looking at the same thing. The first step again is exploratory data analysis. Your first step is to specify what is the output column you're using. Remember, I told you that Y column has to be known because it is used in this particular portion of your modeling approach. So you always have to make sure that you specify what is the output variable you are using. Okay, so this is the output column we are using. The next step is we look at the intercorrelation, because remember guys, I told you that the assumption of linear regression is you need to check for intercorrelation, and df.correlation can help you in that. Suppose 2 features are highly correlated with each other. You have to remove one of them. You have to keep only one of those. Suppose you can set your own threshold. You can set your own definition of what high means. High can be 0.9 also. High can be 0.8 also. High can be 0.95 also. Depends on person to person. Okay. Depends on how practical you want to be. So this is a heat map. It is trying to tell you the lighter number is a higher correlation. So if I zoom in, so you can see bore water injection volume is nicely correlated with on-stream hours, but I'm not sure if it's too high. there are other features. This huge box is a danger zone. So average downhole pressure is very highly correlated with an average downhole temperature. Physically, it is very understandable. Pressure and temperature, pressure increases, temperature increases, something like that during flow. So it's fine, but you need to check in these light zones. Whenever you see light zones, which means two features are intercorrelated with high magnitudes, you need to make sure you keep only one of them. Okay. So you can see from the above metrics that some of the features are fairly interrelated, which breaks the assumptions of linear regression. And hence we might see troubles in our model performance. But let's see if I'm faking all of these assumptions, or does it really break the performance? So let's not trust Divyanshu Vyas here. Let's just go with it for now, and let's fail and then learn, so that you can finally trust me. I don't advertise that I know everything, but I'll prove that I kind of know why this will fail, right? So I just plot the correlation with this thing, and it's a bar plot, nothing but a bar plot. And you can see, don't worry about the syntax. It's just, you can just Google it up and you'll find out. I Google all the time, so it's fine. So I'm trying to figure out what of the features are highly correlated with my output feature, which is the bore oil volume. And you can see bore gas volume is hugely correlated with bore oil volume, which means, unfortunately, my dear friend, I'll have to remove bore gas volume, which makes sense, because why would you predict both oil and gas volume together? If you are already providing gas volume in your data set, you are trying to leak the information, right? And I'll tell you how. I'll just go back to the notebook. I'll go up and show you. So you see the gas volume in the green and the oil volume in the orange. You can see their plots are almost identical to each other because they are produced together, right? Their rates will, of course, almost, I mean, if you dig deeper, you will see that there is difference, but the magnitudes are also different. But the trend that they are following, it's almost similar to each other because they are produced in the same pipe, right? So you need to have only one of these. If you provide gas volume inside as a feature and trying to produce oil volume, your model will ignore all the other features and it will just use gas volume as the input. And you'll find that your model performance is 99.999% accurate, which is not a good news. I wrote a LinkedIn post. I said that if you are a mature data scientist, you will realize that 95% accuracy is a bad thing. I mean, if your model is trying to understand a real world problem, there are rarely any problems which have 95% accuracy in their solution or 0% error in their solution. So always make sure, don't be happy with 90% accuracy. Always make sure you are not leaking information. All right. That's a great advice I'm trying to give you. So you move ahead, you try to drop all these features. Let's say we drop these top 3 features or something like that. And then we move ahead. And again, I'm just looking at these features and I've selected my input features and I've concluded that these are the final input features. You can have your own list of input features, but I have concluded these are my input features. And now I name my input metrics as X, my output metrics as Y, because I know my output column, I know my input columns, and I have 3,300 input data set examples. Okay. So basically this vertical height of my data set is 3,300. Which is fine. I mean, it's not that small also. It's not that great also. Now, this is very important. I have not talked about it yet, but all these calculations and validations that you are trying to do, the gradient descent that you are trying to do, you need to validate this before sending this model to a final software, right? You need to validate whether this model performs good on unseen data set as well. But even if it is unseen, you make predictions. You need also to check whether these predictions are correct. So we do a very smart thing here. We keep some portion of our data untouched. Let's say 20% of the data untouched. We use 80% of the data to do all the calculations that you see on your screen right now. And you make predictions on the left out 20% data and you calculate the error on that 20% data. And that will be unbiased estimation of how good your model was, because those 20% data points, they were almost like unseen. Your model did not train on them. It's like your model did not know the question paper while it was preparing for your examinations. Suppose you prepare for your exam, you have a mathematics exam tomorrow, and you know 3 to 5 20-mark questions out of the 100-mark paper, you will perform well, right? You'll not do terribly on your examination. But some other day, if you are preparing for a physics paper and you know nothing in tomorrow's paper, your results show that you fail, right? So that's your correct estimation of how good you are, right? So that's how we do in the machine learning model as well. The way to do this in time series projects is you keep time-based splitting, okay? If my data is starting from 2004 to 2010, I will take, for training, I will take 2004 to 2008 or 2009, and 1 year I will keep for validation. And that's what I'm doing. And you need to do that for both training and X and Y both, right? So X is this. ILOC is nothing but trying to split out the data from the start to the end. You just provide the starting and the ending of the row, starting and the ending of the column. It's like a slicing of the data set, right? So if you Google how to slice a data frame, you'll find out how to do that, okay? So suppose we have confirmed that I'll be using 3000 for my training, 291 examples for my validation or testing. Then we move ahead. I told you that we need to feature scale also because my magnitude differences are so huge in this data. So I'm using standard scalar in here. So scalar is defined as standard scalar, which we transform the data into X-train scale. Now my data is now very small magnitude. Remember, the trend of the data does not change. The magnitude is not just normalized. Your X-train scale is here, your X-test scale is here. And then you train a machine learning model. You import from sklearn linear model package, we import linear regression. You initialize the linear regression superpowers now by calling them as LM, and you fit lm.fit x comma y. You always pass the training data set in this part of the data, in this step, and then you make predictions off of it, lm.predict, and you pass the training data and you make this prediction. So your orange data is the actual data and the blue lines are the model predictions. And there you go, you see some cases your forecasted or the predicted oil rates are minus 2000. Can you imagine? And not that just that, but a lot of cases your oil rates are in negative. That's a terrible thing, right? Your model clearly did not understand what's happening. Your model was not able to understand that, bro, at least make sure that oil rates are in positives. So again, going back, I told you that our model will fail. And this is our first sign. In training data set, this is only training performance. This is the data that the model has seen. And even on this data, the model is not able to perform well. How will it perform well on the testing data? But still, you still don't trust me. Let's go ahead and make predictions on testing data. The black line is the testing performance. The green dots are the actual testing data. You can see the difference, huge difference. Your original forecasts were pretty low, but your model is saying, sir, I think my predictions should be pretty high. And people will invest based on your decision and you will be in huge loss and you will lose your job. So this is how impactful your decisions can be. So there you go. I confirm that your linear regression problem is not the right fit because some of the assumptions were not followed. Remember, we did not eliminate some of the features here because of the assumptions. So if you go back home, you run the same project, you validate all the assumptions of linear regression on it and follow them, and then run the same model following the assumptions, you'll see that your performance will be better. Okay. But if you don't want to do that, you'll like, I have other algorithms in the world. Why would I want to, spend time on, doing the correct linear regression? That also you can do. You use random forest regressor, one of the best, models in the current scenario, because it does what random forest does is it takes random splits of the data, makes predictions, takes the average, and then returns. Okay. It's like it will take some chunk of the data, run a model, make oil prediction forecast on it. It will make other chunks of the data, run the same predictions on it. And let's say it has 10 such chunks, it will average all of those predictions out. And that will be the final prediction. Of course, some of those predictions will be terrible. Some of them will be highly accurate, but it is looking at the best of all the worlds and the worst of all the worlds. I do not have enough time to cover random forest today, but it is definitely a worth algorithm to check out. So you can see, we don't need to scale data in this. We don't need to do much of this in much of the pre-processing, etc. in this. All you need to do is you just initialize the random forest, you fit the data, you make predictions on the training set, you make predictions on the testing set, you plot it out. You can see how close your model is now to the actual data set, not just in the training, but also in the validation. Okay. But there's still one more improvement you can do. There is a problem here that your data is too noisy. You can do some averaging. You can take 5-day average or 10-day average, which is called resampling. This is an optional task for you guys. You can just create your own cleaner version of this data and run the same model. And you can see the performance. The black line comes even closer to the green line. Right? So that's about my linear regression project. I have just 10 minutes left. I promise that I will cover forecasting for you guys. Let's utilize that and then we will conclude. I'll not take much time from you. Just let me go to, yep. Okay. So that's the final project for today. Oil production forecasting. Everyone knows what linear regression is. Okay. So what we are trying to do is, what if we want to look at the future forecast of my oil production based on my previous versions, previous trend of my oil production? It's kind of a replacement we are trying to make for DCA. Okay. So you can imagine it to be something like that. Okay. So suppose you are owning a shop. Okay. You are owning a shop and you have, let's say, a sweet or a bakery you have, okay, and you are running that bakery from last 10 years, okay, and it's Christmas time in your time, and you want to forecast how much sales am I expecting in this month, in December and January, right? And you have, good thing is you are a data scientist also by the passion, and you have recorded all the data from the last 10 years. So basically, if I go back to my workbook, so if you plot the last 10-year data of your sales, of your cake sales, and you pass last 10 years data, you'll see something like that, something like this. Because the first year you just started, no one knew your shop, you had low sales, but then it went something like this. Okay. And every spike happens at December. Okay. So you have seen that my trend is something like this. You can see my spike is happening in December, and this is your current, now you are in the current present and you want to do some forecast. All you have to do is follow this trend and look at December spike. You just calculate the spike and this is your forecast. Okay. This is the entire philosophy behind what's called forecasting. Okay. And you can do that for, coming times as well. Now, what you have done is you have looked at the previous trend and you have looked at all these spikes. Now replace these trends with the previous trend with a decline and these spikes with shut-ins. Okay. And there you are with your oil forecast problem. I hope I make sense. Every time you shut in, there'll be a spike. And overall, the trend will be declining, let's say exponential decline or something. And when you feed these data points into your model understands all of this, and it understands how the history is behaving. Your machine understands how the things are happening, and it will keep on forecasting based on similar lines. So let me just quickly tell you how this is happening in Python. What we will do is we will create features from the past and store them as additional data points. Okay. So suppose my y is a function of x, right? What if my x was y in the past? Okay. Y is a function of x. That's my regression problem. Now, what if instead of x, I just provide y of past? Okay. So y is a function of my y past. So I have used the regression algorithm to turn it into a forecasting algorithm. All I've done is I've taken y from last 10 days and provided them as features. And I've tried to calculate what is the relation between today's sales or today's oil rate versus the rates of my last 10 days. And I keep on doing this calculation for let's say 10 years, my machine understands the pattern of decline. My machine understands what is the relation between the oil rates of today versus the oil rates of last 2 months. Now, all I need to do is, if I'm standing today, I provide the oil rates of last 2 months to my model. My model will be able to forecast the oil rates for the next 1 week, because that is how I have trained the model as. Okay, so that's my very, very interesting project. People rarely look at this in that way. You can definitely go and check it out. I'm sure it will take much time of yours, because you need to do a bit of math on it. You need to spend, with pen and paper. But definitely worth checking out if you want to get into forecasting. This is the starting step. I've tried to keep it as simple as you can. Before you get into any complex forecasting algorithms, you need to know what's happening in the backend. And this is exactly what's happening. So I've taken one column, which is oil volume, and I've plotted it, nothing else. You can see there's a shut-in happening here or something like that. And there's a spike. I need my machine to understand what is my 2014, what is my oil rate at this point as a function of oil rates of last 3 months. What is my oil rate at 2013 as a function of last 3 months? What is my oil rate at 2012 January as a function of last 3 months? What is my this, and keep on doing that. Okay, I'll have to prepare my data in such a way. That's the biggest task in this. But once I have trained a model in that way, all I need is, if I need to forecast something after this point, all I need to provide is last 3 months of data. And I'll have my forecast generated. It won't be that accurate, but it will be, even if they are 60% accurate, you are still doing a great help, because telling the future is pretty good. I mean, even if it is 50-60% accurate, future is pretty, people accept that. Even if you are 60% accurate in predicting future, you are doing good. Okay. So the way to do it is, you shift the data down, right? You shift the data down and you keep on shifting the data. And I'll show you the final version. You also have to clean the data. This is the cleaner version of the data. I'll show you how the cleaner version of the data looks like. So the shifting is nothing but, you have shifted, let's say Y1. I've shifted the data by 30 days. Okay. Now what's happening here is, I've shifted the data by 30 days. That would mean that my output variable, which is Y1, you can see today's data is located in front of last 30-day back. I mean, January 1 is trained with respect to December 1. What is the oil rate at January 1 as a function of oil rates at December 1? So all you have to do is do a smart thing. You just have to shift the data down. Make sure your Y of today is sitting in front of Y of past, and just train the model, nothing else. I mean, I'm just caught in terms of time, but you definitely have a look at it and I'll show you the results. Okay. You can see the training performance is pretty good. Training performance is still fine, but validation performance we need to look at. Validation is also good enough. This is validation performance. We look at it both together and you can see it's more than 60% accurate, but it is too noisy, but you are almost there. Okay. I told you that DCA, if I had done DCA on this, guys, the DCA would keep on falling like this. It would keep on falling like this. But this is not DCA. This is machine learning. It has its drawbacks, but without us telling it anything about the physics that the machine follows, just a bit of data manipulation, just purely based on data, it is still appearing so close to the actual oil rates. You can see how close it is to the 2015 oil rates. And that's pretty good, given we have not told anything about reservoir physics. This is a machine which knows no petroleum engineering, and it is going to do well. Now, I told you that if you had production data from Antarctica, if you had production data from Moon, this model will perform equally better in all the three cases, unlike decline curve analysis, where it follows from a particular geography only. Right? And when we generate forecast, the good thing is in regression problems, all you could do was have the data where you already had the data, have predictions. Now we can do forecasting. We can generate forecasts from here. We can look into the future. This data only had data up to 2015. Now you can see I will make forecasts also. And let me show you where the forecasts are. You can see the brown line. The green line is the validation part. I was happy with the validation. I was pretty good with the training also. Training, of course, almost always it's 90% accurate. Validation is still fine. It was able to identify the shut-in as well. That's why I went ahead, asked it, tell me the next 2 months of oil forecast, and you can see it is doing pretty good. And now you can trust this model. Okay, so this is how forecasting projects are done. Definitely have a look at it. This is a skill that I have not seen in a lot of petroleum engineers. Forget petroleum engineers. Forecasting is not a cheese of cake. What am I saying? It's not a piece of cake for anyone in the industry. So if you are looking at forecasting, you start at this point, you will be doing great stuff to your resume. Definitely have a check on it. I'll be sharing this entire notebook. I think I'll share it with Stephanie and on my LinkedIn in my feed as well by the end of the day. But this is it. I think we have covered and we are at the end of time. Anyone, we can have discussions now. So much to cover in just 2 hours.
Sorry, one question. What resources, what websites, or what courses would you personally recommend to quickly learn the application of data science? Not diving into theory that much, but actually do something.
Yeah, I mean, if you want to learn from me, definitely follow Petroleum from scratch. So I keep on uploading videos. I, along with my friends, we keep on uploading problems from petroleum engineering. Even if we are explaining NumPy, we use petroleum examples to explain what we are trying to do. So we have, I think, more than 30 to 40 videos on our playlist on YouTube, Petroleum from scratch. So do check that out if you purely want to understand based on petroleum. But other than that, to learn Python, you have Corey Schaffer, you have Krish Nayak, you have a lot of people, good people on LinkedIn and on YouTube. They try to teach you stuff. So definitely, if you don't find anything, do contact me on LinkedIn. I'll send you the links. So a lot of good resources. I mean, definitely you can do Udemy course by Jose Portilla on data science bootcamp. Directly gets you on speed by hands-on exercises. You can do Coursera courses by Andrew Ng and deeplearning.ai and stuff. So yeah, start today, step by step. You'll get to know a lot of things.
Thank you.
I have one question.
Yep.
Regarding unsupervised learning, which other methods would you apply to this data?
So this is not a great candidate for unsupervised learning, but for example, you need to do some clustering, right? You need to do some sort of clustering based on your data. Unsupervised learning can be used in that case where you can use k-means in unsupervised manner. It does nothing, but it just calculates the Euclidean distance between one data point to the other and sees whether some data is lying far away. Then it classifies it into some other cluster, and whichever data points are located in very nearby to each other, they call it one cluster, and it keeps on doing that for every now and then. The common applications of unsupervised clustering are normally in cases, for example, you have geography, you have zip codes, you have lat longs of your geography. You want to cluster these locations based on how close your houses are, right? So that if you are trying to plan your shops, you want to place your shops, you want to see, you can only place 3 shops in a city. Let's say you are owning a franchise, you want to place 3 shops in a city. So you run the zip codes through a clustering algorithms. Your clustering algorithm tells you that there are 3 clusters in this city. You just place the shops on the centers of those 3 clusters. I personally haven't worked a lot, and I've not seen people working a lot with unsupervised problems. But I'll let you know if I have any specific oil and gas example where it can be used.
Oh, sorry. I meant supervised learning. I made a mistake, sorry.
Okay. So supervised learning, was used, right? We are when, okay, I'll give you where the term supervise comes into play. So whenever you see the model.fit, right, the model.fit thing, let me see. Yep, here you are providing X, but you are also providing Y, right? That's what supervise means. If you just provided X, you will see that in k-means clustering, you just provide X, you don't provide Y. It figures out Y on its own. But here you are providing both X and Y. So what's happening here is it will make some predictions based on X. Okay, in the diagram, if you remember this diagram, the black YP is calculated, and then the green Y is what? The green Y is the one that you are providing, the Y train. Okay, and it calculates the delta between both of these, and then it does this gradient descent kind of thing. It calculates error, and then it keeps on doing. So it is a pure example of supervised learning.
And aside from multiple regression and random forest, which other methods would you apply or are your focus of interest?
So if you have a lot of data with you, if you have, let's say, 1 million data points, you can use, definitely try to use artificial neural networks that will give you a great insight. The way I made this diagram, people who have looked at artificial neural network, it is a simple neural network only. This is one neuron only. So it's, if you collect all of these, if you insert multiple layers of calculations between these arrows, it becomes artificial deep, it becomes deep learning. It becomes a neural network. But right now, just because it is a single neuron, it is not a network. But this entire scenario, if your problem statement calls that Y is not linearly related with X, if you have done drilling optimization courses, you will see that there are a lot of correlations which are very